All right, we're in section 11.8. We're going to start talking about power series. So, power series are actually very useful for us in mathematics and in calculus in particular, because what we use power series for typically is representing more complicated series in simpler ways. So complicated expressions and functions, we can represent them much more simply using a power series. So a power series is a series of the form, so it's got a term c sub n and a term x to the n, and we're going n from 0 to infinity. So this would look like c sub 0 plus c1 x to the first plus c2 x squared plus c3 x cubed, etc., etc. And it is an infinite series. This is where x is a variable, and the cn's are coefficients of the series. So they're coefficients. For each fixed x, it is a series of constants that we can test for convergence or divergence. So depending on what the x values are, we can test for convergence and divergence, right? So if well, we'll look at an example in just a sec. So the sum of the power series is a function. Okay, it's this function right here, whose domain is the set of all x for which the series converges. Okay, so the appropriate x values to plug in is anything where it converges. Notice this form represents a polynomial, or I should say it resembles a polynomial, except it has infinitely many terms. Okay, because it's coming from an infinite series. So, for example, if we take the coefficients c sub n to be 1 for all n, the power series becomes the geometric series x to the n. Okay, so it has this form if we let the coefficients all be 1. And then in that case, if we plug in a constant for x is 1/2, then we get a convergent series, right, like this. And then if we plug in x equals 2, for example, we get a divergent series here, divergent geometric series. So in general, when we're looking at power series, so they do have that form that we mentioned, but this is the more general way that we look at them. So we say that a series that has this form, so c sub n, so that coefficient times x minus a to the n. Okay, so that's just the sum with x minus a's increasing in power. This is called a power series in x minus a, also called a power series centered at a, or a power series centered about a. Okay, so different ways of saying that same thing, but this is kind of the general form of the power series that we look at, the power series centered around a. Okay, and then just a brief note, we are going to use the convention that x minus a to the 0 equals 1, even when x equals a. So x minus a to the 0, anything to the 0 power is 1, so we're going with that convention for this series, even if x equals a. Because if x equals a, then actually this series will always be convergent, and so it kind of becomes trivial at that point, because if x equals a, then you get, right, just a convergent, a bunch of zeros being added on thereafter. So that one gives us some information there. So let's look at a couple examples here, and we're gonna start tying these in to our power series. So for what values of x is the series n factorial times x to the n convergent? So in this case, we're gonna go ahead and use the ratio test. Okay, and then we're going to use the ratio test with a sub n, that series, being n factorial times x to the n. Oops. That's n factorial times x to the n. Alright. So, first up, if x is not equal to 0, So let me just put that in here. If x is not equal to 0, then we're going to have the following. So we're going to have the limit, the limit as n approaches infinity of, so a sub n plus 1 over a sub n. So that's the limit, n approaches infinity, of n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. We get some cancellation happening here, and that's why we do this, because it's designed to help get rid of some of those extra factors. So the n factorial cancels with all the terms except the n plus 1 in the numerator. So we're left with just, actually I can shrink this down just a little bit, n plus 1 times x. N is always greater than or equal to 0, so we can take that out of the absolute value. So we have limit as n approaches infinity of n plus 1, but x varies, so we need to keep it inside the absolute value. Okay. And then as n goes towards infinity, that goes towards infinity as well, right? Because n plus 1 heads towards infinity. So we can say, so thus, by the ratio test, the series diverges.
Here are some TV shows.
Whoops.
The Last Ship.
I always forget, because I think this is three days in a row I've forgotten to turn my Siri off. So the series diverges when x is not equal to 0. Now, why do we have the condition that x is not equal to 0? Well, because if we're looking at the series, if x is 0, this whole term doesn't exist, because you have an x in the denominator. So we can't let x equal 0 and test it that way. So we need to treat it as a separate case when x equals 0. But when x equals 0, notice what happens here. We just get 0 to the n, so this is just a big fat 0. And certainly, right, if you just add up a bunch of zeros, you get 0, which is finite, which means it's convergent. So, therefore, the series only converges when x equals 0. Alright. So let's look at the next one. For what values of x does the series x minus 3 to the n over n converge? So we're going to, again, establish our series a sub n. So that's going to be x minus 3 to the n over n. Then our ratio, a n plus 1 over a n. So that's going to be x minus 3 to the n plus 1 over n plus 1. And I'm just going to go ahead and do multiplication by the reciprocal. So that's times n over x minus 3 to the n. So this is going to be, we're going to get all but one of those, canceling with all of those. And again, the n's are all going to be positive, so I'm just going to get those out of the absolute value, like that. So that's what we have. And then this term is still not helpful, so we need to manipulate that. I'm just going to multiply. This is our common trick. I multiply top and bottom by 1 over n. So we're going to get 1 over 1 plus 1 over n times the absolute value of x minus 3, which means that that term turns to 0. So the whole thing is heading towards 1. So this whole value approaches the absolute value of x minus 3 as n goes towards infinity. Okay, so not as clear cut as the last time, right? Last time we had that it headed just off towards infinity, so that made that fairly easy to determine divergence. This time we're heading to a variable value, right, dependent upon x. So we need to look at this a little further. So by the ratio test, the series is absolutely convergent, right, because we're dealing with the absolute value, and thus convergent when the absolute value of x minus 3 is less than 1. And divergent when the absolute value of x minus 3 is greater than 1. There we go. Okay. So we need to look at what x values this gives us. So we can kind of break apart the absolute value into the double cases here. So this one is actually telling us when x is between 2 and 4. Okay, that's what it means. So if you split that into the two inequalities, and this one's saying when x is when x is less than 2 or x is greater than 4. So if you just picture the number line, right? So here's 0, 1, 2, 3, 4. So if we're within this range here, that tells us we're convergent, and anything outside of that range is divergent. Okay, that's what that tells us. All right. So now this gives us what happens when absolute value of x minus 3 is less than 1, when it's greater than 1, but this doesn't tell us anything about what happens when the absolute value is equal to 1. Okay, so what about absolute value of x minus 3 equals 1? Okay, so this is going to give us two cases. It's going to give us the case when x is 2 and when the case when x is 4, right? Because we see that here it's not strictly equal to in any of those. So we need to figure out what's going to happen at that time. So when x equals 2, the series becomes, so if you just plug in 2 for x, it just becomes negative 1 to the n over n. Okay, and then this one is convergent by the alternating series test. All right. So we also get its conversion at 2, so then what about at 4? So when x equals 4, the series becomes just 1 over n, which of course is divergent. Because it's harmonic, right? Or you can say p series with p equal to 1. All right, so what do we have here? We have a series that converges between 2 and 4, and at 2, but not at 4. So thus, the series is convergent for x greater than or equal to 2, I'll add the equal in just a second, and less than 4. Let me just add in or equal to. There we go. So the series is convergent for x equal to 2 or between 2 and 4. Okay, so x between 2 and 4 inclusive of 2, not inclusive of 4. All right. So when we're talking about convergence or divergence of a power series of this form centered at A, there are only 3 possible outcomes when it comes to the convergence of these. So the series could possibly converge only when x equals A. Right? And we saw that it will always converge when x equals A. So, we always have that value. Or it could converge for all x. So it could possibly be convergent everywhere. Or the third option is kind of that in between, or there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r. Okay, now when we say absolute value of x minus a, that represents the distance between x and a. So if the distance between x and a is less than r, it converges. If it's greater than r, it diverges. The number r is called the radius of convergence. Of the power series, and the interval of convergence contains all x values for which the series converges. Okay, so if you just kind of picture, give me my number line here again. So here's the value a, and if we stay within r units, so this is a minus r and this is a plus r, as long as we stay within r units, we are convergent. But as soon as we head outside of that interval of convergence, then we have divergence. Out there and out there. Okay, so that's the basic idea here. Now notice we did not cover what happens at those endpoints. That's because this doesn't give us, those tests don't give us satisfactory solutions at the endpoints. So like you've seen in the last couple examples, we just have to go in and check those by hand. And generally we'll get a series that we can test by itself. Okay? So if we use this theorem, kind of look through this lens at the problems we've done so far. I have a table right here, and I need to fix it because one of these values is wrong. I'm going to fix it on yours before I post it, but mine is not fixed yet. So let me change this. go. Okay. So for the first one, so notice we have the geometric series. So we saw this in the very beginning. We were talking about what the power series is. This has a radius of convergence of 1. And the interval of convergence is negative 1 to 1, right? Because a geometric series is convergent for any value, absolute value of x to the n is, or excuse me, of r, little r in that case, is 1. Right, so that one's between negative 1 and 1. The first example we did, we saw that this one was only convergent when x was 0, so this has a radius of convergence of 0, and the interval of convergence is just a single point. It's just at 0. It's the only place that it's convergent. And then the one we just did, so this one has a radius of convergence of 1, right? If you go back, let's just peek. Okay, so that came from right here. It said that distance is centered around 1, right? Less than 1 or greater than 1. So the radius was 1, and our interval of convergence was between 2 and 4, inclusive of 2. Right, so we saw that just in that example there. All right. So next up, if we're trying to determine the radius of convergence, typically, as you've been seeing here in these examples, the ratio test is usually the way to go. Sometimes the root test will do this for us, but typically it's the ratio test. So we use that to determine the radius of convergence r. However, these always fail, like I said, when x is an endpoint of that interval of convergence, so the endpoints have to be checked with another test. So we have to do those separately. Okay. So now we have a couple examples. So find the radius of convergence and interval of convergence of the series. So first things first, let's just establish our series a sub n. So that's negative 3 to the n times x sub n over root n plus 1. So our ratio, okay, we're going to go ahead and I'm going to turn this into multiplication by the reciprocal as we usually do. So for these complicated ones, I have negative 3 to the n plus 1 times x to the n plus 1 over root n plus 2, right? N plus 1 times the reciprocal of the lower one, so root n plus 1 over negative 3 to the n times x to the n. We get some cancellation here. All of these, all but one of those, all of these, all but one of those. So we have absolute value negative 3x times the square root of n plus 1 over n plus 2. I went ahead and just combined that square root with that one because they're in a quotient, so we can do that. So this gives us absolute value of negative 3 is 3. N's are always positive, so that gives us that, times absolute value of x, because x is variable. Okay. And then so let's rewrite the value in the square root. So multiply by 1 over n to top and bottom. So that's 1 plus 1 over n over 1 plus 2 over n times absolute value of x. Those will turn to zeros, so this just turns into a 1. So this approaches 3 times the absolute value of x as n approaches infinity. Okay. So that's our function in question here. So by the ratio test, the series converges if 3 times the absolute value of x is less than 1, and diverges if 3 times the absolute value of x is greater than 1. Okay. So when we're looking at kind of rewriting these in a way that better suits our needs, so 3 root x less than 1, that's equivalent to just writing absolute value of x less than 1/3. And this one we can just write absolute value of x greater than 1/3. Okay, so that's what we're really looking at here. We have convergence when the absolute value of x is less than 1/3, and divergence when the absolute value of x is greater than 1/3. Okay, so we know the series converges on the interval negative 1/3, comma 1/3. Okay, so it converges on that interval, but what about at the endpoints? Oops. So we need to take into account what happens at those endpoints, at negative 1/3 and at 1/3, to really determine the true convergence of this series. So let's go ahead and break these into cases here. So if x equals negative 1/3, then our series is going to look like negative 3 to the n times negative 1/3 to the n over root n plus 1, which is the sum. Remember, n going from 0 to infinity. You can combine those values in the numerator because they share the same power, so this just becomes 1 over square root of n plus 1, with n going from 0 to infinity, so this looks like 1 over root 1 plus 1 over root 2 plus 1 over root 3, etc. Hopefully this one might look kind of familiar. We've worked with series like this. I think we've even worked with this series before. This is a p series, with p being 1/2. Okay, so we know that that is divergent. So this is, which is divergent. Okay, so when x is negative 1/3, we have the series is divergent. So then let's look at the one remaining case. So if x equals positive 1/3, then our series is going to become, so we have the series negative 3 to the n times positive 1/3 to the n over the square root of n plus 1. Okay, so we get this sum, and going from 0 to infinity of, in this case, we get negative 1 to the n over root n plus 1. And this one is actually convergent by the alternating series test, so which is convergent by the alternating series test. Alright, so we get that that one is convergent. So thus, the power series that we've been looking at is convergent from negative 1/3 to 1/3, but inclusive of 1/3. So the interval of convergence is negative 1/3 to 1/3, inclusive of 1/3. All right. So you can see these examples take up a bit of time, right? We have to go kind of through these arguments step by step, but we're just testing convergence basically 3 times here. So you test the convergence of the series as a whole. That gives you, right, R, that R value, the radius of convergence. And then we have, did I not put that in there? Huh, what do you know? I didn't put that in there. That was what it was asking for, right? Let me sneak back into the problem here. Sorry about that. Probably like, wait, you didn't answer the question. Yeah, so we saw right here the series converges if the absolute value of x is less than 1/3. What that tells us is that the radius of convergence is 1/3. Okay, so we have, so thus the radius of convergence is R equals 1/3. Okay, so you can just take note of that. So the radius of convergence is 1/3. The interval of convergence is negative 1/3 to positive 1/3. Okay. All right. So let's do one more, just so we can really get the hang of this. But you're going to notice the pattern here. A lot of these are getting treated the same way when we're solving them. So find the radius of convergence and interval of convergence of this series. So let's establish our series a sub n. That's n times x plus 2 to the n over 3 to the n plus 1. So again, we're going to look at the ratio of these. So we're going to get n plus 1 times x plus 2 to the n plus 1 over 3 to the n plus 2. And I'll do times the reciprocal, so times 3 to the n plus 1 over n times x plus 2 to the n. Get some cancellation here, so all of those x plus 2's will cancel with all but one of those. All of those n plus 1 3's will cancel with all but one of those. So we're left with absolute value of n plus 1 times x plus 2 over 3n. So everything can come out of the absolute value except for the x plus 2. So we can do, so I'm going to group this. I'm going to group the n plus 1 over n right here, because the n's are all positive, times absolute value of x plus 2 over the 3. Okay. The n plus 1 over n, you can split that up, so that's just going to be 1 plus 1 over n times absolute value of x plus 2 over 3. As n goes towards infinity, that goes to 0, so this whole thing heads to 1, so it ends up not impacting. So we get, this approaches absolute value of x plus 2 over 3 as n goes towards infinity. So again, we have this condition, this variable condition here. So using the ratio test, the series converges if we have the absolute value of x plus 2 over 3 is less than 1, and diverges if we have the absolute value of x plus 2 over 3 is greater than 1. Alright, so those are our two conditions. If we go ahead and multiply both sides by the 3, alright, this will give us absolute value of x plus 2 less than 3. Alright, absolute value of x plus 2 greater than 3. Okay. So, since this is the term that we're looking at, comparing against that absolute value, that distance, we can then say, thus, the radius of convergence is r equals 3. Because we're centered around 3 here. Okay, or I should say that distance is less than or greater than 3. That's where we're looking. So that radius, that distance away from x. Alright, so now we need to find those endpoints. Alright, so we can write the absolute value of x minus 3, or excuse me, x plus 2. Where did my plus go? Oh, there it is. X plus 2. So we can write that that is less than 3. So we can write that as x being between -5 and 1. So -5 less than x less than 1. So we'll need to test the series. Oops. At the endpoints. X equals -5 and x equals 1. Okay, so let's go ahead and do that. So when x equals -5, we have the sum of n times -3 to the n, right? -5 plus 2 over square root of n plus 1, or excuse me, got my problems mixed up. This is 3 to the n plus 1. Alright, so this one, we would get an extra factor of 3 down here in the bottom, so I'll just pull that out. So that's 1/3 times the sum of -1 to the n times n. Okay, and then this one, as n goes towards infinity, this is just going to keep growing and growing and growing. We can test this using the test for divergence, so which diverges by the test for divergence. Okay, so that's when x equals -5. So then let's check the other endpoint. So when x equals 1, we get the sum of n times 3 to the n, right, x plus 1, or x plus 2, excuse me, over 3 to the n plus 1. So this is just 1/3 times the sum of n, right? 1 times n, which is certainly going to be divergent, right? Because n is just going to grow and grow and grow. Okay, so which also diverges by the test for divergence. Alright, so we got that the power series is going to converge between -5 and 1, right? That's what we got from that absolute value. But we checked the endpoints, it does not converge at the endpoints. So we can go ahead and conclude. So thus, the interval of convergence is -5 to 1, not inclusive of -5 or of 1. Alright, so that brings us to the end of section 11.8, so the introduction on our discussion of power series. So when we come back next time, we're going to be looking more at power series and then start talking about other types of series as well. But we're almost done, just a couple more sections in chapter 11, so let's finish strong, and I'll talk to you all next time.